Dr. Ranjani Parthasarathi is a professor in the Department of Information Science and Technology, Anna University. Her area of specialization is computer architecture and networks. One of her special interests is Indian language technology systems. She is actively involved in research in all the areas and has over 50 publications to her credit. She has about 25 years of experience covering both industry and academics.
Welcome to the UGC lecture series in computer science. This is a series of lectures on computer architecture. So, we have been looking at the memory subunit and particularly at the cache organization. So, we have looked at direct mapped cache and we have looked at the performance of direct mapped cache. So, what we will now look at today, two other mappings, which is fully associative mapping and set associative mapping, and performance considerations with respect to those two. So, recollect the 4 cache questions that we have talked about, because this is what we will use to understand caches again. Where can a block be placed in the cache, which is the placement strategy? How is a block found if it is in the cache, the identification strategy? Which block should be replaced, cache miss, which is the replacement strategy? And what happens on a write, which is the write strategy? So, placement, identification, replacement and write, 4 strategies. Okay. So, now let us look at these questions with respect to placement. First, we start with the placement strategies. Again, we already know that there is something called a direct mapped cache, which we have looked at in detail. And then we said there are 2 other mappings possible, fully associative mapping and the set associative mapping. In fully associative mapping, we said any block can go anywhere in the cache, as opposed to direct mapping where there is only one choice. In set associative mapping, we divide the cache into different sets, and we said that the block can go anywhere in a restricted set of places, that is within a set it can go anywhere. Okay, so, let us look at how this works. So, take a look at this picture here. So, in a direct mapped cache, okay, let us say we have 8 blocks here. Okay. So, a particular cache block, okay, let us say block number 12. Okay. This block maps only into this position 4, this is the only place where it can go. In a set associative mapping, right. So, what we do is we divide the cache into different sets. So, let us say each set has 2 blocks. Okay. So, there are 4 sets that we have 0, 1, 2 and 3, and within the set it could be anywhere. Okay. But which set it will map onto, that is fixed based on the address that you have here, okay, the block address. So, what do we do? There will be tags associated with each of the blocks. Now, what I need to do therefore is, which of the tags do I need to search to see if there is a match? Within the set I have to search for both these tags, because there are 2 blocks into which this particular block can go, right. It can be placed in one of these 2 positions. So, in which position is it present? To understand that, I have to search these 2 blocks that are available within that given set. I identify the set number based on the address that I have. Okay. That identification is done in a manner similar to what we use for direct mapped cache. Now, once we have identified the set number, within the set it can go anywhere. So, I need to search both these tags and find out that yes, 12 is over here, this matches my block that I am looking for, therefore, this is the block that I am looking for. This is the set associative mapping. In fully associative mapping, we said it can go anywhere, right. So, which means given a particular address, I will have to search the tags of all the different blocks that are available. Remember that there is a tag which is associated with every block that we have. So, now because it can be anywhere, to find out where it is, I have to do a comparison with all the tags present in my cache block. Okay. So, that is the fully associative mapping. So, as you can see, to identify where it is, the search is very simple in the case of direct map, because there is only one location that I need to look for. In fully associative, it is very complicated, because I have to search the entire set of tags. Set associative, you can see, is somewhere in between these 2, because here there are limited set of places where I need to do the comparison. Okay. So, these are the 3 options that we have: direct mapped, fully associative and set associative mapping. Okay. So, now we will look at fully associative and set associative in detail. Okay. So, if you look at the fully associative mapping, we say that it allows a given block to go in any cache entry, any block in the cache, and as we saw, it requires that all entries be searched at once. Okay. So, remember this complete comparison, you have to do it at the same time. If you are doing it in sequence, then your comparison itself will take a long time. Therefore, your fully associative cache access will take too much time. So, in order for your fully associative cache to be fast enough, we have to make sure that all these comparisons are done simultaneously. So, it requires that all entries be searched at once, which obviously means that for every entry we need to have a comparator, okay, which is what makes your fully associative cache a little more expensive. So, why a comparator per entry? Because we need to do all the comparisons simultaneously, okay, that makes it a little more expensive. Now, if you look at the set associative cache, now we normally talk about a n-way set associative cache. What does n indicate? It basically indicates the number of entries that are there in each set. Okay. In the example that we just looked at previously, there were 2 entries in each set. So, this actually is a 2-way set associative cache. Okay. So, now what we are talking about is, in general we can talk about an n-way set associative cache. So, what is an n-way set associative cache? It indicates that each set can have n entries. To identify which set you need to look for, you look at the block number, that is, the block number determines which set has to be used. So, we take the block number and do a modulo operation with respect to the number of sets in the cache. Okay, we know how many sets are there in the cache because we will know how many entries are there in every set. So, if we say we go for a 2-way set associative memory, and if you have say 16 blocks in your cache, so how many sets will be there altogether? 16 divided by 2, there will be 8 sets in the cache. Okay. So, I will do a block number modulo number of sets in the cache to identify which set I need to look for. Okay. And within that set you will search for all entries at once at the same time. Okay. So, how many comparators will I need? Number of comparators I need is dependent on the number of entries which are there in each set. If it is an n-way set associative cache, I will need n comparators. So, as you can see, this will be less expensive than the fully associative option. This is what we need to understand with respect to fully associative and n-way set associative caches. So, if you look at the spectrum of associativity as we call it, right, that is, you can see that fully associative is one end, direct mapped is another end, and set associative comes somewhere in between. So, to understand this, let us just look at this picture. We have a whole range of associativity that we can look at. Okay. So, if you look at your direct mapped cache, you can call it a one-way set associative cache. Right? There is only one block in each set. Okay. So, that is your one-way set associative is one end of the spectrum, is your direct mapped cache. Now, let us understand it from a 8 block cache. Okay. Our cache has got 8 blocks. Okay. So, one-way set associative, which is direct mapped, every block is a different set. So, there are 8 different blocks that are available. Now, let us look at the same thing organized as a 2-way set associative cache. So, what would we do in this case? Here, since it is a 2-way set associative, which means every set has got 2 different blocks. Okay. So, how many sets will I have? I will have 4 sets. Given that my total size is 8, I will have 4 sets, each set having 2 different blocks. So, now since there are 2 blocks, for every block of course I will have its own tag. Okay. So, this is my 2-way set associative mapping of my 8 blocks that I have. Next, I can look at the same thing organized as a 4-way set associative cache. Okay. So, let us look at this, a 4-way set associative cache. Now, same 8 blocks. So, I divide it into 2 sets because each set now has got 4 different blocks in it. Okay. So, there will be only 2 sets that you will identify, set 0 or set 1, but within the set there are 4 positions where it can go into. Okay. So, you can see that there is more flexibility here. It can go into any one of these 4 positions. The last one that we have is our fully associative cache or a 8-way set associative cache, where you can see that it is only one set, right. All the blocks are in the same set. Okay. So, it is 8-way set associative cache, there are only 8 blocks. So, there is only one set, and I will have to do a comparison with all the tags that are there in this particular set. Okay. So, you can see the spectrum of associativity that we have. You can go from a one-way set associative to a fully set associative cache. Okay. So, this gives us our direct mapped cache one end, this is our fully associative cache the other end, and then you have different n-way set associative caches in between. Okay. So, these are different choices that we have, and as you can see, direct mapped will be the simplest, fully associative will be the most expensive, and our 2-way and 4-way set associatives will be somewhere in between these. This is the range of associativity that we can look at. Now, we will continue and look at the different associative mappings will behave when we have a sequence of memory accesses that are taking place. Okay. So, let us look at this example where I have a series of accesses, say 0, 8, 0, 6 and 8. Okay. I am looking at a 4 block cache, a simple 4 block cache. So, I have got 4 blocks 0, 1, 2 and 3. Okay. So, let us say for instance, the block address that we have, okay, is 0, 8, 0, 6 and 8, and we look at the cache index. Now, this is the example for a direct mapped cache. Now, we remember we are comparing direct mapped, fully associative and set associative. So, direct mapped cache, if we look at block address 0, now remember we have only 4 blocks in the cache. So, 0, if you do a mod function with respect to 4, you will get your value as 0. So, cache index will be 0. Initially there will be a miss, okay. So, mem 0 will come in this position. Now, let us say next block being accessed is, we said is 8. So, 8 again will map into the same position, cache index 0, because 8 mod 4 will give me 0 again. So, this again will be a miss and it will replace this 0 with this 8. Again if 0 is being accessed, look at what will happen, same cache index 0. So, again this will come and replace the same entries here. So, again you will get a miss, okay. See, actually there are enough empty spaces here, but we can't put them here because of our direct mapping approach where it will only map into a particular position. Next, let us say the block being accessed is 6. So, 6 mod 4 you will get 2, again a miss, okay, but now it will come into position 2 here. Now, next cache being accessed is 8. So, 8 mod 4 0, again it will come over here because 0 is what is over here, therefore, one more miss and you will get this block replacing your 0th block. Okay, so, you can see for this particular sequence with a direct mapped cache you would have got all misses, 5 misses. Okay, this is what happens in a direct mapped cache. Now, let us look at a two-way set associative cache for the same sequence of operations. So, 0, 8, 0, 6 and 8. So, block address 0, it is a two-way set associative cache, so which means it is going to map into only 2 sets, set 0 or set 1. Okay, so, I will do a mod 2 operation. So, 0 mod 2 will give me cache index as 0, it is a miss. Now, so it will go into set 0, but in set 0 it can go into any of these positions. So, both are empty, so it can go into one position. So, let us say mem 0 goes here. Next, what I do is, next my block being addressed is 8. So, 8 mod 2 again index is 0, it is a miss, but I have one more position here. So, I will put this block in this particular empty slot here. So, in set 0, mem 0, mem 8 both the slots are filled. Next 0 is being accessed, okay, index is 0. Now, I know that it is already there. So, this is a hit for me, okay. So, mem 0 this is a hit. So, I get a hit over here, so no problem. Next is 6. Now, remember block address 6 when you do a mod 2 again will map into cache index as 0. So, this is again a miss, not there in the cache, and now this has to replace something, okay. So, let us say it replaces block number 8, okay. It could have replaced either of these two, but let us say we replaced block number 8. If it replaced block number 8, so now you have overwritten 8 with 6. Now, next the block address is block being addressed is 8, again 8 mod 2 is 0, so miss again because it is not there, and therefore it will come and replace the next entry, let us say 0, okay. So, you got 1 hit and 4 misses in this case for a two-way set associative cache. Of course, here if we had replaced 0 instead of 6, we might have had one more hit, okay, one less miss is what we could have had. Again, it will depend on which block you are replacing within the cache. So, it depends on the replacement policy. We will look at that later, okay. But generally you can understand that, and you can generally see that with a two-way set associative, okay, the number of hits will generally increase, okay, number of misses will decrease. So, we will take a short break and then continue with the fully associative case. Welcome back after the break. So, we were looking at this example of a series of block addresses being accessed. So, we looked at the direct mapped cache and we looked at the set associative cache. Now, let us look at the fully associative cache. So, fully associative cache, it can, now we have 4 blocks, right. So, it can go anywhere. So, block number 0 gives a miss, can go anywhere. So, let us say we put it over here. Now, block number 8, it is a miss again, empty places are there in the cache. So, it goes into the next block, let us say. Now, block number 0 already it has been there in the cache. So, we get a hit. So, mem 0 it gets accessed over here. Now, block number 6 now it is a miss, not there in the cache, but it can now come and sit in another empty slot. Block number 8 being accessed again, so it is there in the cache, therefore it is a hit, okay. So, it is that will be accessed. So, you can see when you have a fully associative cache, number of hits will increase, number of misses will decrease, because you do not have the same thing replacing something else when there are empty slots that are available in the cache. Okay. You can see that in both the other cases, both set associative and in the case of direct mapped, even though there are empty slots, we had some blocks coming in replacing already existing entries. Okay. That is what we will avoid when we go in for a fully associative cache. Okay. But as we have already seen, fully associative caches are a little more expensive. So, we kind of mostly go in for a set associative option. Okay. So, the question therefore that always we look at is how much of associativity. So, we know that fully associative is good, and but it is expensive. So, we have to go in for some kind of a set associativity. So, how much of associativity we need to look at. Okay. So, to do that, if you look at a study of miss rates, okay, it's found that increased associativity does decrease the miss rates, but with diminishing returns. That is, if you look at for instance a simulation study which was done on a 64 kilobyte cache, data cache with 16 word blocks, spec 2000, this is a particular benchmark set of programs that was used for doing this study. So, they found that with one way set associative, which is your direct map, right, you get about 10.3% miss rate, two way you get 8.6%, four way 8.3%, 8 way 8.1%. So, you can see that the decrease as you go from 2 way to 4 way to 8 way is not very significant. So, which means you will get almost similar performance even if you go for a 4 way or an 8 way cache in general. Okay. So, normally you will find that many caches use about 4 way set associative or an 8 way set associative cache. Okay. So, that is how the associativity is normally determined. Okay. Now, we will take a look at the organization of these caches. So, we talked about what they will, how the performance will be, but we also need to understand how it will be organized. Okay. So, we will take a look at the fully associative cache organization. If you look at how the cache would look like, so as we said, the cache will be divided into blocks, right, and for each block you will have a tag that is associated with it. So, number of blocks, for each block there will be a tag. So, as you can see, every set of blocks will have a tag associated with it, and given your memory address basically will be divided into two portions, a tag portion and a word portion. So, the tag will be the one that is compared with all these different tags that are coming from here. So, you will have a set of comparators, okay, which will compare this tag with the different tags that are over here, and if it matches, if any one of them match, you have a hit in the cache, and so you take the data from that particular block. If it is not there, then we get a miss in the cache. You will have a miss in the cache, and if you have a miss in the cache, then we need to go and get it from the main memory. Okay. So, that is what we do. Main memory will be accessed if there is a miss in the cache. What is important to note here is how this comparison is done and how the memory address is divided into the tag and the word. Okay. So, this is what we need to understand from the organization here. So, if you look at our address structure, okay, as we said, there will be a tag portion and a word portion. So, let us take another example here. So, let us say we have a 22-bit tag stored with each 32-bit block of data, alright. So, then, so how would your data field basically look like? We are looking basically at a 24-bit address that we are looking at. So, 2 bits are used to identify the word which is there within the block, okay. So, 32-bit block of data, so you can look at it as 4 8-bit words, okay. So, 2 bits is what we require to identify which word we are looking at, and 22 bits will be the tag. So, remember what happens in every access, you will be comparing this tag field with the tag entry in the cache to check for a hit, okay. And then we use the least significant 2 bits to identify which particular 8-bit word in that block is being accessed, okay. So, for example, if you had and the address is FFFFFFC, okay, the tag that you would have would be the 22 bits over here. So, remember C is 1100, okay. So, 00 will be the one that is used to identify the word. So, your 22 bits FFFFF and C 11, okay, all this will form your tag bits, and whatever data is over there, that particular cache line will be accessed, okay. This is what will happen in the case of a fully associative mapping. If you had a set associative mapping, okay, now what will happen, your entire address field will be divided into 3 parts. Why do we need 3 parts? Because we need to identify which set it is and then identify within that set which particular block it is. That is done with the help of the tag field, okay. So, we have 3 fields here, tag field, set field and the word field. Okay. So, again if we assume a 24-bit address that we have, so let us say we have a block with 4 words in it. So, 2 bits will be again used to identify the word in the block, okay, and depending on the number of sets that we have. Okay, how do we determine the number of sets? We have already seen this, right. Number of sets is determined by looking at number of blocks in the cache and dividing it by the associativity that we have. Okay. So, now assume that we are having 2 power 13 sets. Okay. So, 13 bits will be there in your set field. The rest of the bits that we have, so 13 plus 2, 15 bits are used for set and word. So, out of 24 bits now 9 bits are left out, so that will form your tag field. Okay. So, 9 bits for tag, 13 bits for the set and 2 bits for the word. So, this is what we use to identify now which block we need to look at. So, we will use a set field to determine which cache set to look in, and then we will do a tag comparison to see if we have a hit. Okay. So, for instance in this example, if there are 2 addresses, these are 2 addresses 1FF 7FFC and 001 7FFC. So, how will you identify the set field in this? You have to look for the 13 bits starting from the 3rd bit position. The first bit and the second bit you will leave out because they are your word bit position. So, starting from the 3rd bit position, 13 bit positions you will take to identify the set. So, that is from, if you look at these 2 addresses, you will find that both of them are mapping to the same set, because if you look at the 7FFC, okay, that is where your last 15 bits are there. Leave out the last 2 bits, start from the 3rd bit onwards and take the 13 bits. The address that you get, number you will get will be 1FFF. 1FFF will be the number that you get. Okay. The rest of them will form your tag field, that is your 1FF will be your tag, these 3 bits 001 will be the tag for this address. So, 1FF will be the tag for this block, 001 will be the tag for this block, the set number for both of them will be 1FFF. Okay. So, by looking at the set number you will identify that this particular set, within that set you will do a comparison with the tag and identify which is the data that you need to pick up. Okay. That is what happens in the case of set associative mapping. So, if you look at the organization for a set associative cache, this is what we will have. Okay. So, again address is divided into 3 parts, right. So, we have a data within the block, and then this is your identification of the set, and this is the tag field that we have. So, set identification, if we call that as the index. So, this is an example where I have a 4-way set associative cache. So, you can see what is happening here. So, we will identify the set by means of this set field here, the index. Okay. So, we have in this example I am showing 8 bits here. So, which means I can go 2 power 8, there are 256 different sets available. So, 256 different sets, identification of a particular set is done by means of this field here, and then all the blocks in that particular set will all be accessed simultaneously. Okay. So, each of them, the tag fields of each of these fellows will be taken and compared with the tag field coming from your address. So, you can see that there are 4 comparisons that are going to take place simultaneously. Okay, this is your comparator, a comparator here, a comparator here and a comparator here. 4 comparisons will take place simultaneously, and then assuming that you will also check for the valid bit. If the tags match and the valid bit is set, then that indicates a hit. So, one of these 4 will give you a hit, right. So, you do an OR of all these 4 and then you get your hit. If you get a hit, depending on which one is giving you a hit, you will take the data from that. So, you have a 4:1 multiplexer to take the data from one of these particular blocks, and that will be your data. Okay. So, this is basically how your n-way set associative cache will be organized. Okay. So, we looked at organization of the cache, we looked at how the placement is done with respect to fully associative and set associative. Now, coming to the replacement policy. So, we know that in direct mapped cache there was no choice, we always had to replace only particular block, but in the set associative cache, okay, you have a choice, because if an n-way set associative, there are n different positions. Okay. So, which one do I replace? Okay. If all of them are full, only then you are going to do a replacement. If there is an empty place, you are going to use the empty place. So, but if all the blocks in the set are full, then we need to worry about which one we need to replace. Normally, which one would you prefer? If there is a non-valid entry, then you will prefer that. Otherwise, we choose among the entries in the set using some policy. Okay. So, what are the policies that we have? Commonly used policies are least recently used. So, what do I mean by least recently used? Because I choose the one that has been unused for the longest amount of time. So, idea is it is not been used for a long amount of time, not likely to be used again. So, I can replace that particular entry. Okay. So, this can be done very simply by using some kind of a small counter and some kind of a timestamp. Okay. This is actually very easy if you are looking at two-way set associative cache and so on, and also for four-way, but beyond that it becomes little difficult to manage. Okay. This is for the least recently used. Second option that we have is the first in first out policy, again similar to least recently used, but here what we do is here we go based on which was the first to come in. So, that is the first, that is the one that we will throw out first. Okay. First in first out is another replacement policy. A third policy is what is called as a random replacement policy. Okay. That what we are talking about in random replacement is that any block at random we will choose and we will replace it. Okay. What is very surprising is that it has been found that random replacement gives you almost similar performance as LRU when you have very high associativity. Okay. So, this is study that has been done based on again some experiments and simulations, and they have found that random replacement gives you as good a performance as least recently used. And random replacement is also easy to implement because you just pick up any one at random. It is very easy to generate one random number in hardware. Therefore, random replacement is normally a policy that is used in many of the cache organizations. Okay, this is with respect to the replacement policy. Now, coming to write strategy, we could either use write through or write back. Okay. Normally, write back is the one that is preferred in many cases, both for set associative and fully associative caches. Okay. So, that is how the fully associative and set associative caches function. So, to summarize, so what all we have looked at in today's lecture is the following. So, you looked at fully associative cache and set associative cache. We looked at the range of associativity that is possible, okay, how we can go from direct mapped to all the way up to fully associative. We have looked at the address structures for both these cases and how the cache is organized. We also looked at the replacement options that are available. Okay. So, this is what we have looked at in today's lecture. Okay. So, questions to go over the material today. Question number 1, why do we go for associative caches? Question number 2, which gives you more flexibility, set associative or fully associative? Question number 3, for an 8K cache with 1024 blocks with 8 bytes in each block, show the address structure for a 32-bit address for a fully associative organization and a 4-way set associative organization. So, you will have to give which is the tag field, which are the bits that will be used for the tag field, which are the bits that are used for the set field and so on. Okay. Question number 4, list the cache replacement options. Thank you.